Hello teachers, welcome to a new chapter. This is chapter 12 where we're going to talk about congruence and similarity with constructions. So we're going to talk about how shapes are congruent and similar, which does mean two different things we're going to define very quickly. And when we talk about constructions, we're talking about creating shapes, line segments, angles, bisectors using a compass and a straight edge only. Now, constructions will be great for both you and your students to understand these theorems in geometry. In 12-1, we're going to talk about congruence through constructions. That's the name of the section. Students will be able to understand and explain geometric construction leading to the, now this says SSS, which represents side, side, side. The second one, SAS, is side, angle, side. And HL is hypotenuse leg congruence properties. We'll discuss all those in detail. We're going to talk about isosceles triangle properties, altitudes and perpendicular bisectors, and circles circumscribing triangles. So first, let's talk about congruence and similarity. What do these definitions actually mean? Similar objects, and notice the notations, just little squiggly lines. Similar objects have the same shape, but not necessarily the same size. Picture in your mind a triangle that has exactly the same shape as another triangle, but 5 times bigger, right? That is completely possible, to have the exact same shape, but not the same size. The same thing with a square. We can draw a teeny tiny square, and we can draw an enormous square, and they have the same shape, but not the same size. On the other hand, congruent objects, and notice the notation there, you've got an equal with a squiggly line, okay? Congruent objects have the same shape and the same size. So we spend a lot of time in this section talking about congruent objects, and again, that notation is very important as well. Congruent objects are similar, okay? They're similar, so congruent does imply similarity, but similar objects are not necessarily congruent at all, okay? So definition this time, congruent segments and angles. So notice the notation here. Again, congruent segments, these are line segments we're talking about. So line segment AB is congruent to line segment CD if and only if, remember that means you can read it both ways, AB equals to CD. Now you need to know that this notation, AB equals to CD, is their measure. So the length. Now remember the original definition said line segments were congruent if you can place one right on top of the other. If you could trace one right on top of the other. That really implies they're the same length. Okay, because remember, line segments actually don't take up any space at all. They're just a line with no area at all. It's just to represent a part of a line. So if they are the same length, which is what this second notation is saying, then they are congruent. Angles are the same way. So you can say angle ABC is congruent to angle DEF, and that's how you would read that. If and only if the measure of angle ABC is equal to the measure of angle DEF. So notice that the difference in notation, they don't put an M in front of the line segment to say the measure. That AB without the line over it just means the length of AB, and CD without the line just means the length of CD, whereas angle, they'll put an M in front. So that's the measure of angle ABC equals the measure of angle DEF. Now, back in the day, Euclid of Alexandria, he lived 300 BCE, so we're talking 2,300 plus years ago, wrote a mathematical work called The Elements, and he defined what a point was, he defined what a line was, and he used a few axioms and constructions to develop pretty much all of geometry. So the things that we're talking about today and in other sections about geometry Euclid developed. Now, Elements was not just geometry. Elements had arithmetic and some algebra in there. And this is not the first we've talked about Euclid either. In Math 231, we use a Euclidean algorithm to calculate the greatest common divisor of two numbers. And so Euclid has done a lot in math. Well, these are rules for Euclidean constructions. So number one, given 2 points, a unique straight line can be drawn containing the points as well as a unique segment connecting the points. You could do that with a straight edge, and Euclid believed that you could draw all of these constructions with a straight edge, not even a ruler. It doesn't have to be marked, with a straight edge and a compass. Okay, you know what a compass is, right? It's got that point and then the other end holds a pencil. You need one. Okay, so given 2 points, a unique straight line can be drawn containing the points as well as a unique segment connecting the points. A circle can be drawn given its center and radius. Okay, so you need a compass for that, and you also need a compass to measure the length of your straight line. Number 3, any number of points can be chosen on a given line, segment, or circle. And the 4th, points of intersection of 2 lines or 2 circles or a line and a circle can be used to construct segments, lines, or circles. And that 4th principle really is what you use to build your constructions, all 4 of these actually. Now here's our first construction, but what I want to let you know is I have a link in your Canvas course called Constructions, and these are short little videos from the textbook that tell you how to do all the constructions that I'm going to include. So I'm not going to spend a huge amount of time talking about the constructions in this video. If the steps that are shown here don't make sense, or you want a video to see someone doing these constructions, it is available. Okay, so please look those up. Constructing a circle given its center and radius. So the first thing is we are given, okay, a center and a radius. So you have to have these 2 things to construct a circle. Okay, next box. All right, so set the legs of the compass on P and Q to obtain PQ. So you're trying to obtain this length, and you see how they set the compass up. Okay, your point doesn't necessarily have to be on Q or P, as long as you get that length. Now make sure you do not move that opening. That opening stays fixed. Okay, then you come over in the second step. It says set the pointer at 0, which is the center opening of the compass. So notice that the pointy part is right here at the center, and then you have kept that opening that you measured over here, and then you just trace your circle. So hold the pointer at 0 or O and move the pencil to draw the circle. It takes practice drawing a circle with a compass, and you've got to make sure that your pencil is in the right spot. If it's too short, it's not going to work right, or if it's too long, it's not going to work right. It needs to be the same length when it's closed. Okay, take some practice. Make sure you practice this. And this construction is about drawing a line segment. Now, as you can imagine, there's lots of ways to draw a line segment. You could use a ruler, but if you're trying to do true constructions, a straight edge and a compass is all you have. You don't have a ruler, but you could measure using a ruler. You could trace the line segment. You know, you have a thin piece of paper, you trace on top of the line segment you can see below. And the method shown here is again with a straight edge and a compass. So the first thing you do to copy A, B on any line. So here we have this line segment and we're trying to copy it on line L. Now how could you create line L? You could just draw it with a straight edge, right? Or you may already have it. It just depends on your situation. Now the next thing you do is you measure it with your compass, just like we measured the radius of our circle before. You can measure here, all right, and you move the compass over to your line and you draw an arc. Okay, you see this little arc here? Remember, a compass draws a circle. There's the arc right there, and from your point C to your point D that measures AB. So place the point of the compass at any point C on L and strike an arc to locate D. And then now CD is congruent to AB. They're exactly the same length. Now let's talk about congruence of a triangle. Okay, two figures are congruent if it is possible to fit one figure on the other so that matching parts coincide. Just like a line segment, if you could fit it on top of the other one, a tracing on top of the other one, you know they're congruent. Same thing with figures. Notice it doesn't even say two triangles. This is any figure if you can match it up perfectly on top. But you don't always have that convenience, so you need to be able to determine if one triangle is congruent to another triangle with other ways, and that's what we're going to talk about. The notation is terribly important, and really that's what this page is about. So if you'll notice, here we have angle A right here. Notice the notation. It's got the arc with two lines. That corresponds to A primed over here. Okay, those correspond to each other. What else corresponds to each other? Look at angle B over here. It's an arc with three lines. That corresponds to B primed in my other triangle. Those are the same measure. And also, angle C was the arc with one line, corresponds to C primed over here with the arc with one line. But not only that, the sides. Look, the single mark corresponds to the single mark. So side AB corresponds to A primed to B primed. Side BC with the double lines corresponds to B primed, C primed, and then AC corresponds to A primed, C primed. But how you write this up, notice A in the first position corresponds to A primed in the second position, okay? Angle B corresponds to B primed, and C corresponds to C primed. They have to be in the same order of their congruence. Now, what does that really mean? Triangle ABC is congruent to triangle A prime, B prime, C primed, written as, notice the notation, that triangle ABC is congruent to A primed, B primed, C primed, if and only if all of these things are true. So what the first thing says here is what we listed, that angle A is congruent to A prime. They're the same measure. Angle B is congruent to B prime. They're the same measure. Angle C is congruent to C prime. They're the same measure. But not only that, the lengths of the sides are the same as well. So line segment AB is congruent to A prime, B primed. Line segment BC is congruent to B prime, C primed. And finally, the third side is congruent. So what this means is corresponding parts of congruent triangles are congruent. And that's what we wrote above. So if I know triangle ABC is congruent to A prime, B prime, C prime, then I know all of these things. Each angle is congruent to its respective angle. Each side is congruent to its respective side. Now we have a problem. Finally, example 1, write an appropriate symbolic congruence for each of the pairs. So it's two different problems. Let's look at problem A to start with. So we need to pay attention to what angles match. Okay. Now the way you may want to start this is to first just write the first triangle. Okay. So we have triangle. And I'm just going to write it as A, B, C. Okay, we're going to try to say it's congruent to the other triangle. Now, I'm just not going to write F, D, E, or E, F, D, or D, E, F. No, that's not what I'm going to do. I have to match up congruent sides. So we started with A, B. Let's find that same side in this triangle. Can we even say that? Well, let's take a look. 4, this is length 4, so I'm going to put the one little mark here, matches that side. The 3 length side corresponds with this side right here, and assuming these are congruent, we're not even sure about that now, I'm assuming that from the given problem, that this side across here, and we call that a hypotenuse, right? The side across from a 90-degree angle, that side is going to correspond to this side. So I'm looking at AB here, okay, and over here that is EF. Now do I write it as FE or do I write it as EF? Well, I started with A, and that's connected to the 3-link side. E is connected to the 3-link side, so we're going to go from E to F to D. Again, if I picked up this triangle and I slid it on top of this one, you see that the B corresponds with the F. Notice they're in the same position down here. The A corresponds with the E. They're in the same position also. And that the C, which is the right angle, corresponds to D, which is the right angle over here. Okay, and I've got this typed up as well. And there is triangle ABC is congruent to triangle EFD. Now, let's go back and look at my notation, which really bites. I started with the angle symbol, and so that's not correct. I just wasn't paying attention to what I was doing. And I didn't even put a triangle over here. Okay, and again, that's the argument for having these answers typed up, right? So proper notation, triangle ABC, not angle ABC, is congruent to triangle EFD. Okay, now let's try this again. As a matter of fact, why don't you pause the video and see if you can do a similar thing for question B. Assume these are congruent triangles. I want you to set up the appropriate notation to show that they are congruent. All right, how did it go? Okay, so proper notation. So we're going to say triangle. We're going to get your pen to work. All right, so triangle. Now, we could say ABC again. That's perfectly fine. When you're looking at the first one, really, you want to wrap around in order, often from, clockwise, but that's kind of up to you. Clockwise is a good way to do it. So I did A, B, C. Now, how about corresponding sides? So notice that CB or BC is the same as PQ. Okay, so I could even write that at the end. There's PQ. So from B to C, the way I've got it listed, is the same as from P to Q. Is that right? Or is it Q to P? What do you think? Now, I would argue that actually, when you look at that, it is from, if we're going from B to C, that's going from Q to P. So I'm going to say that's Q to P. Correct? And then the hypotenuse, notice that is AB, okay? And it's going down to the angle that's 30 degrees here, okay? So that's going to be from R to Q. And I get my triangle in front of there. So I could say triangle ABC corresponds to triangle RQP. Now notice they said Q was 30 degrees here. That would mean B is 30 degrees here, but it didn't say so. But it is, right? Because this is 90 and this is 60. 90 plus 60 is 150. That leaves 30 degrees. Remember, every triangle adds to 180 degrees, the angle measures. So over here, this one's 30, then this one is the 60. Now make sure your angles correspond. A is 60 degrees, R is 60 degrees. Notice A and R are in the same position. B is 30 degrees, Q is 30 degrees, B and Q are in the same position, C is 90 degrees, P is 90 degrees, C and P are in the same position. Okay? All right, so let's just check our answer. And have triangle ABC and RQP. Is that what we had before? Yes, that's exactly what we had before. Now, we have our first theorem of congruence. To be able to tell if one triangle is congruent to another triangle, you don't necessarily have to check all 3 angles and all 3 sides. If you do, you are positive they're congruent if it all matches up. But you can just check 3 sides. So if 3 sides of one triangle are congruent to respectively to 3 sides of a second triangle, then the triangles are congruent. So you can show congruence by something called SSS, or side, side, side. So let's look at a problem. Example 2. It says use side, side, side to explain why the given triangles are congruent. And remember the other problem, we weren't trying to prove congruence. We were just trying to set up the relationship by using the proper notation. Now we're actually trying to prove congruence, and since we have a theorem that says we can use just the three sides, I believe we've got it, right? Can we show that these three sides are congruent? It's like, sure we can. Look, AB right here, okay, and DE are the same length. So I could say line segment AB is actually, well, let's just use congruent. It's congruent to line segment. Now, do I say AB, do I say DE, or do I say ED? Okay. Now I say, look, so here's 3, here's 3. The 4 is across from that. So if we say ABC, if we keep it in that order, ABC triangle, then it goes from A to B is my 3 side, B to C is my 2 side. So this would need to go from ED to get to F. Okay, so ED. Now, they may say DE, but I try to keep it in the proper order of the congruence of the triangle. So AB is congruent to ED. Well, let's check out our 2 side, okay? So our 2 length and our 2 length right here. So I can also say BC corresponds to, so we're going from B to C, so that's from D to F. BC corresponds to DF, and they're congruent, okay? And then over here, are the 4s congruent? Well, sure they are. They're both length 4, okay? And that's CA that I have listed there, so I could say side CA is congruent to side, okay? So I'm saying C then A, so coming from the 2 side, okay, that's going to be FE. So we have, see here, that side, side, side. So because of side, 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 we can say that triangle ABC is congruent to triangle, remember, we're going to get this order right, EDF. And again, check it, make sure it matches. So is angle A the same as angle E? In the picture, that's between sides 3 and 4, it's between sides 3 and 4, yes. Is angle B the same as angle D? Okay, so angle B is between 3 and 2, angle D is between 3 and 2. And is angle C the same as angle F, is the way we have it depicted, and C is between 2 and 4, and F is between 2 and 4. So I argue this is it. Okay, we showed it, and if we look at the typed up version, just kind of written horizontally, a little bit more confusing, but they're trying to get the job done. They have ABC is congruent to triangle EDF. And that's exactly what we have. Now I have a part B for you to take a look at. Why don't you pause it and see if you can do the same thing, side, side, side. Show that these correspond to each other, and then we can show that these 2 triangles are congruent, and make sure you write it out just like we did the one before. Now once again, I suggest picking an order to write your triangle in. So we're going to say triangle, I'm doing this at the bottom, I'm going to write above, ABC again. So ABC. So let's take a look. We're going to try to say that's congruent to. Now we're going to figure out how to order this by doing the problem. So you see that AB here is the same length as, do I say BD or do I say DB? Well, if we look at the corresponding sides, okay, let's try this again. So AB, and then let's look at the bottom, AC, or let's do BC next. We did this in this order. So AB, okay, corresponds to, or is congruent to side. Now, again, do I say BD or do I say DB? Now, if I'm starting with the bottom A up to B, I'm going to say this is D up to B, okay? DB. And that's showing one side is congruent. Now, let's look at, next I have BC written down here, so let's go B to C. So BC is congruent to, now if I look at it on the other triangle, if I'm going from D to B, and that's still BC also. Can we say those are congruent? Of course they can. They're the same, right? So a side length is always congruent to itself. So that's another side. And then we're going BC, so then we're going back from C to A. So it goes from A to B, B to C, and then C back to A. So C to A, okay, is side length CA the same as side length CD? And I argue there are, because they're both 5, right? So we have shown by side, 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 then these are congruent. Now, how do I write my triangle down here? What order did I do it in? I went DBC. So congruent to triangle DBC. Now let's look at their answer. And I'm just looking at the conclusion. ABC is congruent to triangle DBC. That's exactly what we did, and we showed each of those side lengths are the same. So you're kind of getting the hang of it now? Good, I hope so, because we've got something else to talk about. So constructing a triangle given 3 sides. So we're back to constructions. We're back to your straight edge and your compass only. Please watch the videos for these. I think you'll find it very helpful to see this in real time, someone doing this. But how do we do this? What if we are given a triangle and we need to copy an exact construction of that? And we're going to do it using the side, side, side method. Okay, so that's the method we just used to prove that one triangle is congruent to another. We did it twice. Well, now we're going to do a construction based on the side, side, side method. So first it says construct line segment A prime C prime congruent to AC. So basically what you're doing is you're using your straight edge and your compass to draw this line right there. Okay, how do you do that? You put your pointer at A and you measure the length C, and then you have a straight line drawn down here, a line with your straight edge, and you mark a point for A and put your point on your compass there and draw a little arc to measure C. Okay, that's something we've already talked about doing. What do you do next? Okay, it says locate the vertex B primed by constructing 2 circles whose radii are congruent to A, B, and CB. So let me explain this. So you're going to take your point on your compass, put it on A, and mark that length B right there, and then come over and put it on A primed and draw an entire circle. That's that big circle. Okay, then you're going to do the same thing. You're going to come back over here and put your pointy part of your compass on C and mark that length right there. Measure it, mark it, come over to C primed and draw that circle right there. Here's what's cool. Do you see what's going on? Where those 2 circles intersect, and here's the arcs right here, then you draw with your straight edge your lines right there. Notice how it also does a reflection of that triangle. If you draw the full circle, often you'll see people just put the arcs right there where they cross each other, so you know where B primed goes, okay, that vertex of B. But you could do a reflection of that as well by drawing the full circles. Really neat construction. Now, it's very important to know the triangle inequality, because it helps to know if a triangle could even exist. So it says the sum of the measures of any 2 sides of a triangle must be greater than the measure of the third side. What does that mean? Well, let's look at some examples, right? So it's saying that, look at this first triangle. What's the longest side over here? It looks like that one right there. So it's saying that if you add the other 2 sides, so for instance 4 centimeters plus 6 centimeters has got to be greater than the other side of 8 centimeters. So this is a possible triangle. The one that's drawn here is really something that's actually possible. But that's not the only inequality. You could also add 4 plus 8 is 12. That's got to be bigger than 6. or 6 plus 8 is 14 has got to be bigger than 4. But really, you want to look at the longest side because that's the one that makes the most sense. Come over here, check this out. So this side is 3 centimeters and this side is 5 centimeters. So what this triangle inequality says that 3 plus 5 has got to be bigger than the other side that's 9. It's not. What does that mean? It means this triangle is not drawn right. It's a faux triangle. It is not real. Okay, this is not possible. The 9 side would actually not make it down to meet the 3 centimeters over here. So this guy is not possible. You will find problems like this in your homework. You have to use the triangle inequality to check it out. Okay, I've reached my 30-minute mark. I like to make these videos not so crazy long so you can have a breather in between. I am going to come back for part 2 of this. We're going to talk about some more construction, and we're even going to talk about more congruence theorems. I hope you have a wonderful day and reach out if you're having problems.